Hello everyone. In this lesson, we will discuss the first derivative test. Our objective is to find the minimum and maximums of functions using the first derivative test. Another way of calling minima and maxima, we call these extrema. The first derivative test. Suppose that f is a continuous function over an interval I containing a critical point C. If f is differentiable over I, except possibly at a point C, then f of C satisfies one of the following descriptions. 1. If f prime changes sign from positive when x is less than C to negative when x is greater than C, then f of C is a relative maximum of f. 2. If f prime changes sign from negative when x is less than C to positive when x is greater than C, then f of C is a relative minimum of f. 3. If f prime has the same sign for x less than C and x greater than C, then f of C is neither a relative maximum nor a relative minimum. Now let us look at a problem-solving strategy for the first derivative test. Consider the function f that is continuous over an interval I. 1. Find all the critical points of f and divide the interval I into smaller intervals using the critical points as endpoints. 2. Analyze the sign of f prime on each of the subintervals. If f prime is continuous over a given subinterval, which is typically the case, then the sign of f prime in that subinterval does not change and therefore can be determined by choosing an arbitrary test point x in that subinterval and by evaluating the sign of f prime at that test point. Use the sign analysis to determine whether f is increasing or decreasing over that interval. 3. Use the first derivative test and the results of test 2 to determine whether f has a local maximum, local minimum, or neither at each of the critical points. Another way of saying local maximum is to say relative maximum. A local minimum is also called relative minimum. Let us look at an example. Find the relative extrema of the function f of x is equal to 1/2 x minus sine of x in the interval 0 to 2 pi. Now notice here, when we say relative extrema, we are looking for a relative maximum or a relative minimum. The interval is restricted to 0 to 2 pi because, as you know, the sine function is really a function that has numerous maximum and minimum. So that is why we need only to find the answers or the solutions within this interval 0 to 2 pi. Let us look at a solution for this problem. Our function f of x is equal to 1/2 x minus sine of x on the interval 0 to 2 pi. Find f prime of x and set it equal to 0. F prime of x be equal to 1/2 minus cosine of x. We set this 1/2 minus cosine of x is equal to 0. Then try to solve for x. Algebraically, then cosine of x will be equal to 1/2. We want to find angles in the interval 0 to 2 pi whose cosine is 1/2. Those angles are x equals pi over 3 and 5 pi over 3 in that interval 0 to 2 pi. Now we want to set up subintervals between these two critical numbers, pi over 3 and 5 pi over 3, where we can do our test points. So we have to think about, let's see a number line where there's a pi over 3 here and a 5 pi over 3 there. And test points in the intervals, let's say between 0 to pi over 3, we can pick pi over 4. Between pi over 3 and 5 pi over 3, we can pick the test point pi. And to the right of 5 pi over 3, we pick the test point 7 pi over 4. Take each of these test points and plug them into your f prime of x function, which was 1/2 minus cosine of x. And when we plug in pi over 4, we will get a negative number for our sine of f prime, so that's going to be negative. We plug in pi, f prime of pi will give you a positive number. And when you plug in 7 pi over 4, the f prime of 7 pi over 4 will be a negative number. So we can make a conclusion about our f of x function, whether or not it's increasing or decreasing. On the interval 0 to pi over 3, because our f prime is negative, then the function is decreasing. On the interval pi over 3 to 5 pi over 3, because f prime of x, or f prime of our test point, was positive, then on that interval the function is increasing. And on the interval between 5 pi over 3 and 2 pi, because the f prime of our test point, 7 pi over 4, was negative, then all along the interval the function is decreasing. So what can we say then? Let's apply our first derivative test. By our first derivative test, at x equals pi over 3, notice what is happening. It is decreasing before it gets to pi over 3, and then increasing afterwards, which means that we have bottomed out at pi over 3. So then at x equals pi over 3, f has a relative minimum. What about at 5 pi over 3? Notice before 5 pi over 3, it was increasing and then decreasing afterwards. So the opposite is happening here. At x equals 5 pi over 3, f has a relative maximum. And that is how you use your first derivative test to check for the extrema on a function, a differentiable function. You take the derivative, set it is equal to 0, use those critical points as your boundaries for setting up your intervals, then choose test points within those interval tests, whether they're positive or negative, by plugging them into your derivative function, and then make a conclusion based on the signs that you get from the derivative function. Make a conclusion about f. And then finally, look at what is happening before and after the critical points. If it is decreasing, then increasing, then you have a minimum. And if it is increasing and then decreasing, then you have a maximum. Let us consider an application of the first derivative test to a real-life problem. The position function of a particle is given by s of t is equal to t cubed minus 5t squared plus 2t for t is greater than or equal to 0. A. Determine the velocity function of the particle. B. Determine the intervals when the function is moving in the positive direction, or when the particle, it should be when the particle is moving in the positive direction. And part C, determine the intervals when the particle is moving in the negative direction. And part D, determine the times when the particle is changing direction. Let's try to solve this problem. Our original function, or position function, s of t was equal to t cubed minus 5t squared plus 2t for t greater than or equal to 0. We want to find the velocity function. The velocity function is the derivative of the position function. So v of t is equal to s prime of t. We take the derivative of t cubed, that's going to give us 3t squared. 5t squared will give us 10t, and 2t gives us 2. So our velocity function will be 3t squared minus 10t plus 2. We're going to set up our structure for the answers to B, C, and D by looking at what we did previously with our first derivative test. Let's find the critical numbers of this function. Find the critical numbers. We set v of t is equal to 0. V of t was our derivative function, so that's just setting the derivative equal to 0 and solving for t. 3t squared minus 10t plus 2 is equal to 0. It's not easy to factor this function, so let us use a quadratic formula. So if we remember what the quadratic formula says, it says something like x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So if we use a t representative of our x, and we think about a, b, and c, where a was 3, b was negative 10, and c was 2, and just use these numbers. So t will be equal to negative of negative 10 plus or minus the square root of negative 10 squared minus 4 times 3 times 2 all over 2 times 3. And try to simplify this as much as we can. Negative of negative 10 is a positive 10 plus or minus square root of negative 10 all squared is 100. 4 times 3 times, that's 12 times 2, that's 24. 2 times 3 is equal to 6. And then one more simplification. T will be equal to 5 plus or minus radical 19 over 3. Then we want to look at 5 plus radical 19 over 3 and 5 minus radical 19 over 3 as our boundary points. Okay, those are critical values, so that would be boundary points for our interval. So between 0 and 5 minus radical 19 over 3, that's an interval. 5 minus radical 19 over 3 to 5 plus radical 19 over 3, that's an interval. And then 5 plus radical 19 over 3 and up, that's our other interval. Test points, we can choose 0, 1, and 5 and plug these into our derivative formula. The sign of v of t, v of 0 is greater than 0, so that's positive. V of 1 is less than 0, and v of 5 is greater than 0. Just plug in each of these numbers into your derivative function. And so conclusion about s of t is increasing, then decreasing on the second interval, and increasing on the third interval. So for part B, the particle is moving in the positive direction wherever the function is increasing. So that's on the time interval 0 to 5 minus radical 19 over 3, and 5 plus radical 19 over 3 to infinity. The particle is moving in the negative direction wherever the function is decreasing, and that is on the time interval 5 minus radical 19 over 3 to 5 plus radical 19 over 3. And for part D, the particle changes direction at the critical points. Notice it's going from increasing to decreasing at 5 minus radical 19 over 3 and decreasing to increasing at 5 plus radical 19 over 3. So at those 2 points, the particle is changing direction from positive to negative. Thank you for watching, like and subscribe, and see you next lesson.